of matter. All right, so we start with solids first of all. You know what are solids? Solid is a state of matter that is having definite volume and shape. Okay, solid is a state of matter that is having definite volume and shape. You all are aware of this. So solids, for example, sugar crystals are there, and this wood is there, glass is there, all these are solids, right? Further, there are two types of solids also, crystalline. Just for your knowledge I am telling you, otherwise these topics are not directly covered, okay, not directly included in the syllabus, but just for your knowledge. There are two types of solids, crystalline and amorphous. Crystalline solids, they have some definite 3D pattern. They have some definite repetition of one unit over and over. So they are symmetrical arrangements of molecules. And amorphous solids, they in this irregular arrangement of atoms will be there, right? For example, glass. Glass is an amorphous solid. It is brittle. Crystalline solid like sugar is there, quartz is there. These are crystalline solids. All right. So let us come to elasticity. What is the property of elasticity of solids? Elasticity. For example, I have a rubber band. Okay, I stretch it a little and then release it. What will happen? It will regain its original shape and size. Now I increase the force a little and release it. Again, it will come back to original position. So this is the property of solids due to which any solid regains its original position and shape back when the deforming forces are released. That is called elasticity. So write down the definition of elasticity. Write down. Elasticity is the property of a solid due to which it regains original shape or size when deforming forces are removed. Obviously, deforming forces were applied first of all, and after the removal of deforming forces, if the body regains original shape and size, then it will be called elastic body, and this property of solid is called elasticity. So I repeat the definition once again. It is the property of a solid due to which it regains original shape and size when deforming forces are removed. All right. So this is the property of elastic. There are some substances that you can't stretch at all. They are not elastic at all. For example, wood is there, plastic is there. So those bodies, they are called plastic objects. Okay, elastic objects are rubber is the biggest example. Steel is also very elastic. Otherwise, it doesn't appear to be. But steel is even more elastic than rubber. We will prove it later on, right? So this is the property of elasticity of a solid. So how can we define elastic bodies? Elastic bodies. So these are the objects which recover completely their original configuration on removal of deforming forces. They are called elastic bodies. तो जो अपनी original shape and configuration को पूरा completely recover कर लेती हैं, regain कर लेती हैं when we remove the deforming forces, these bodies are called elastic bodies. Okay, so I repeat, elastic bodies, the objects which recover completely their original configuration. Configuration includes both shape and size. Their original configuration on removal of deforming forces. So you can write examples as I told you, rubber and steel. These are the examples of elastic objects. If we talk about perfectly elastic bodies, perfectly elastic, what do we mean by perfectly elastic objects? That regain original configuration immediately and completely after the removal of deforming forces. There is no delay, like rubber band is there, right? जैसे ही हमने force लगाया छोड़ा वो साथ ही अपनी original shape पे आ जाता है. So it is perfectly elastic. उससे भी ज़्यादा रबर से भी ज्यादा किसको हम perfectly elastic consider करते हैं? Quartz fiber and phosphor bronze fibers. Phosphor bronze. But they are also not 100% you can say perfectly elastic objects. 100% नहीं कह सकते. They are nearly perfectly elastic. You can say quartz fiber and phosphor bronze fiber, they are nearly perfectly elastic bodies. So what are perfectly elastic bodies? They regain original configuration completely and immediately after the removal of deforming forces. So add this word immediately. So I hope this concept, these definitions are clear to you. And plastic bodies that don't regain original shape and size after the removal of deforming forces because of their structure is like that. Okay, and rather they break if we try to stretch them. So examples are plastic, wax, clay, glass. You can write these examples. Okay. Now we have different terms because Hooke's law is in our syllabus. So for doing Hooke's law, we need to understand two terms, stress and strain. So first of all, let's understand what do we mean by stress. Stress, आपको पता ही है, pressure को ही कह देते हैं हम stress, ठीक है? So when deforming forces are acting on a body, then restoring forces that try to recover original shape and configuration. So these deforming forces or these restoring forces acting per unit area of the object, they are called stress. ठीक है? Basically stress is pressure. तो रहना तो वही है कि force over area. But the question is which force here we are talking about? Deforming force भी हो सकता है, and in the answer to deforming force, always restoring forces are produced in elastic objects. Because I told you what is the cause of elasticity. The cause of elasticity is the internal structure of such objects. Their molecules, you can say, they are in the form of springs. Suppose we are taking an elastic substance, cause of elasticity, I am telling you before we proceed further. So their molecules, they have coiled structures. Okay, they have spring-like structures, coiled structures. And when deforming forces are applied on them, what will happen? These springs will get stretched. These springs will extend. Okay, and you know what is the property of a spring? Always restoring forces are produced within the springs. Those restoring forces try to bring back the object to original shape and size. So what is the cause of elasticity of a substance? The coiled structure of its molecules. So these spring-like structures, they extend when deforming forces are applied. And restoring forces are produced within those restoring forces, they restore original shape and size of the object. So those restoring forces are responsible for the property of elasticity of any object. All right. So let us define stress that way. So stress is defined as deforming force acting on an object per unit area, or since restoring force will always be equal in magnitude to deforming force, we can also say restoring force per unit area. Restoring force per unit area. So you can define stress in two ways. Both ways are correct. So basically stress is restoring force acting per unit area of the deformed object. And in equilibrium, restoring forces are always equal to deforming forces. So we have both the definitions. All right. Then what is the unit, what is the dimension of stress? Same as that of pressure. So unit of stress is Newton per meter square, or you will see in books Pascal is also given. And the dimension is m1 L minus 1 T minus 2, same as that of pressure. So stress and pressure, they have same dimensions, identical units. All right. Now, types of stress. Depending upon the direction of force acting, there are two types of stress. There are two types of stress depending upon the direction of force acting. Normal stress, if the force is acting normally on the surface. If the stress is acting normally on the surface, then the stress will be normal, right? So let us consider any object, any surface. Let us assume any force acting on the surface. Resolve this force into two components, two rectangular components. Let us say this is theta. Then this component must be F cos theta. This component must be F sin theta. Can you tell me which one is the normal component? Which component is normal to the surface? F sin theta. So when we are writing normal stress, it will be normal force per unit area. Suppose area of the object is A. So normal force per unit area, that is called normal stress. So in this case, in this particular example, it is F sin theta upon A. In this particular example, it is F sin theta upon A. One example from the practical life. Suppose you suspend a wire from the ceiling. Okay, its weight is acting in the downward direction, perpendicular to it. So you will say in this case normal stress is acting on the wire. So if we suspend a wire even freely, it will, what will happen? A stress will be acting on it on account of its weight even, because that weight is normal to its length. Okay. Second type of stress is tangential stress. Tangential stress. So by the name it is clear, it is the ratio of tangential force per unit area. It is the ratio of tangential force per unit area. So in this particular example, the tangential component of force is F cos theta. So we'll better write F cos theta upon A. Okay. I give you a practical example of tangential force. Suppose you have a skeleton cube, only walls are there, and base is fixed. Suppose this base is fixed to the table. Okay. If you pull its upper face tangentially, अगर आप सिर्फ upper face को tangentially pull करो, तो it will get tilted through an angle. It will get tilted through an angle. Okay, and this force that is acting, that is tangential force. In this case, the force acting was tangential force. So I hope the two types of stress are clear to you. Normal stress, tangential stress, depending upon the direction of force, very simple. Okay, any doubt you can raise hand. यहां तक कोई डाउट है तो बच्चे पूछ सकते हो. है किसी को डाउट? हाँ जी गितेश बोलो.
मैम ये रिपीट कर दो टेंजेंशियल फोर्स.
ओके. Tangential stress means tangential force acting per unit area. Okay, it is the force which is acting along the tangent, which is acting parallel to the surface. So in this case, which force is acting parallel to the surface? F cos theta. So we will write F cos theta upon. This is just an example I have given you कि suppose कर लो आपके पास एक क्यूब है जो स्टिक्स से बना हुआ है, स्केलेटन क्यूब है, ठीक है, उसका बेस हमने फिक्स कर दिया, तो वो थोड़ी सी ऐसे स्ट्रक्चर होगी. आप उसके टॉप फेस को जब पुल करोगे तो वो आप उसको टेंजेंशियली पुल कर रहे हो, पैरेलल पुल कर रहे हो टू इट्स अपर फेस. तो इन दैट केस द स्ट्रेस एक्टिंग इज टेंजेंशियल स्ट्रेस. ठीक है, ये क्यूब टिल्ट हो जाएगा थ्रू सर्टेन एंगल. ये जस्ट मैंने आपको वैसे एग्जांपल दिया है. Otherwise, that particular example is sufficient to define these types of stress. Then we come to strain. Next term after stress is strain. Dimensions में पढ़ा हुआ है आपने. Strain had no dimension. ठीक है ना. Strain की कोई dimension नहीं थी, ये याद होगा आपको. So what is strain? It is defined as change in configuration per unit original configuration. Change in configuration of any object when the deforming forces are applied. तो उसकी configuration change हो रही है, उसकी shape change हो रही है, उसका size change हो रहा है. तो कितना change है per unit original configuration? Per unit original configuration. So this change may be in length also, this change may be in area also, this change may be in volume also, maybe in shape also, right? So we sum up in all these things in one term, that is configuration. Okay, so write down the definition of strain. Basically, it is the ratio of change in configuration to the original configuration when a stress is applied on any object. Deforming forces are applied means we are applying stress, and because of that stress some strain, some change is being produced in the object. So that change in configuration per unit original configuration, that is called strain. Now there are three types of strain. There are three types of strain: longitudinal strain, volumetric strain, and shear strain. This shear strain has been deleted, but even then I'll tell you a little bit about it. Rather, I have discussed. ये वही angle है through which the cube gets tilted when a tangential stress is applied on that cube. तो वो जिस angle के through वो tilt हो रहा है, all the four walls of cube they get tilted through which angle? That is called shear strain. ठीक है? It is the angle through which a cube gets tilted when tangential stress is applied on it. So let us concentrate on the two types, first two types, longitudinal strain and volumetric strain. So first is longitudinal strain. By the name it is clear, longitudinal strain accounts for change in length. When length of any object changes and normal stress is applied on it. Again we are taking a wire, it's always cylindrical, so let me show it like that. It is a cylindrical wire suspended vertically. Okay, now I told you the stress acting on it under its own weight is normal here. So its original length was L, suppose. Under the effect of its weight, it gets extended. Its length increases through a factor of delta L, and new length becomes L plus delta L. So what is the change in length here? That is delta L. So how will define longitudinal strain? It is defined as change in length per unit original length, and this will happen when a normal stress is acting on it. Longitudinal strain is defined as the ratio of change in length per unit original length. So it is obviously delta L by L. Delta L upon L. So note down the expression for longitudinal strain. Delta L by L. Then, is that clear? Any doubt? Then we come to the next type, that is volumetric strain. Volumetric strain. Okay, so this volumetric strain is equal to change in volume. By the name it is clear. Here what is changing? Volume is changing. So it is change in volume per unit original volume. And let us imagine a situation in which this is happening. Suppose an object is there, okay, and a stress is acting, a pressure is acting normally on all the sides. Okay, this is normal stress P acting from all the sides, trying to compress the object. ठीक है, तो suppose under the action of the stress from all the sides, its original volume was V, it decreases through delta V. Its new volume becomes V minus delta V. Minus sign shows that the volume is decreasing here. So volumetric strain will be change in volume delta V per unit original volume, and it would be negative in this case. Negative sign would show that it is decreasing, volume is decreasing. So this is volumetric strain, and in this case also the stress is normal. Okay, so we have defined both the terms stress and strain, and now we are using these terms to define modulus of elasticity after we state Hooke's law. So our next topic is Hooke's law. यहाँ तक कोई doubt? You can raise hand if you are having any doubt, students. पूछ लीजिए. Stress की types, strain की types clear हैं आपको? What is elasticity? What is the cause of elasticity? Is that clear to you? Okay.
Excuse me, ma'am.
So next topic is Hooke's law. Hooke's law. Will
Excuse
anybody
me,
tell
ma'am.
me what is the previous form of Hooke's law that you did so far? In unit 1 you have already done. When you did spring balance ना, वहाँ पे आप ये करते हो कि it is based on Hooke's law. Who will tell me that old form of Hooke's law? Raise hand. We are going to do the modern form of Hooke's law, but before that you must be aware of what is the old form, what is the previous form of Hooke's law. Yes, raise hands if anyone knows. It also forms the principle of spring balance. Yes, anybody? Very simple this is. बहुत ही सिंपल है, आता होगा आपको, फॉर्मूला भी आता होगा, हमने उससे डायमेंशंस भी कैलकुलेट किए हैं, स्प्रिंग कांस्टेंट के की, स्प्रिंग कांस्टेंट, फोर्स कांस्टेंट और स्टिफनेस कांस्टेंट के. यूजिंग हुक्स फॉर्मूला यू हैव ऑलरेडी कैलकुलेटेड इट्स डायमेंशंस. यस, कम अप, रेज हैंड, हु कैन टेल मी. किसी को नहीं पता बच्चे? चलो मैं आपको याद कराती हूँ कि जब हम एक स्प्रिंग को एक्सटेंड करते हैं, उस पर लोड अप्लाई करते हैं, देन द एक्सटेंशन प्रोड्यूस्ड इज डायरेक्टली प्रोपोर्शनल टू द लोड अप्लाइड. ओके, और द रिस्टोरिंग फोर्स इज directly proportional to the extension produced in the spring. So F is equal to, F is proportional to F, F is minus Kx. We introduce spring constant K. Do you remember now? So the restoring force produced in a spring is directly proportional to extension. पर applied force extension की direction में होता है, restoring force उसकी opposite direction में होता है. That's why we put a negative sign here. So you have recalled this is Hooke's law, previous form. Now we are going to do the modern form of Hooke's law. It states that within elastic limit, stress is directly proportional to strain. Now what do we mean by within elastic limit? अब एक पॉइंट ऐसा आता है, आप रबर बैंड को स्ट्रेच करते हो, ठीक है, इट कम्स बैक, बट व्हेन यू एक्सटेंड इट, स्ट्रेच इट बियॉन्ड लिमिट, कि ये अपनी ओरिजिनल शेप को रीगेन कर ही नहीं पाता, वो परमानेंटली डिफॉर्म हो जाता है, ठीक है, दैट मीन्स इट इज आउट ऑफ इट्स इलास्टिक लिमिट. सो वी आर टॉकिंग अबाउट दिस लॉ विल रिमेन वैलिड विद इन इलास्टिक लिमिट. जब तक ऑब्जेक्ट अपने ओरिजिनल शेप और साइज को रीगेन कर रही है, तब तक ये लॉ वैलिड है. So write down the statement of Hooke's law. Within elastic limit, stress is directly proportional to strain. Within elastic limit, stress is directly proportional to strain, and when we divide this, there is a constant stress upon strain, that is equal to constant, and that constant is called modulus of elasticity. So the ratio of stress to strain, that is called modulus of elasticity. Remember this. Okay, so modulus of elasticity will have dimensions of stress only, because strain is dimensionless, unitless. It is change in length over original length. It is change in volume over original volume. So strain is unitless, dimensionless. So modulus of elasticity will also be having the dimensions or units of stress only or pressure only. All right, students, is that clear? Any doubt? So Hooke's law statement is clear. Modulus of elasticity definition is also clear to you. It is the ratio of stress to strain. How do we define modulus of elasticity? Ratio of stress to strain. Now, depending upon different types of stress and strain, we have three types of moduli of elasticity. Types of modulus of elasticity. Plural of modulus is moduli. M-O-D-U-L-I-I. Right. So first one is Young's modulus. First type is Young's modulus, denoted by symbol Y. Second type is bulk modulus, denoted by symbol K. And third type is modulus of rigidity, denoted by symbol eta. Modulus of rigidity, denoted by symbol eta. And this has been deleted. This third type has been deleted from the syllabus, because this is also called shear modulus. So in the deleted topics, they have given this term shear modulus, that has been deleted. Okay, because the strain involved in this case is shear strain, that angle theta. So this third type is not included. Even then I'll tell you the definition, right? So we are mainly concerned with first two types, Young's modulus and bulk modulus. Any doubt up to here? Yes, students, any doubts? No doubt? Okay. So let us define Young's modulus, the first type. We know basically modulus is the ratio of stress to strain, but which type of stress and which type of strain? So Young's modulus is the ratio of normal stress to longitudinal strain. First type of stress and first type of strain. And which situation, which example is applicable here? The same, this example is applicable. A cylindrical wire being suspended, and in this case normal force is acting, that is its weight mg, and change in length is delta L. So new length is L plus delta L. So in this case normal stress can be written as normal force over area. नॉर्मल स्ट्रेस क्या होता है, हमने डेफिनेशन की थी, नॉर्मल फोर्स अपॉन एरिया. शुभी इज एंटरिंग नाउ. So normal stress is normal force per unit area, and longitudinal strain. And what is longitudinal strain? That is, we have already calculated in this case delta L over L. Longitudinal strain is delta L by L. We had defined it already by taking the same situation. Fine. So FL over A delta L. And in this case, the force is weight. So we write mgl, and area of cross section of this circular, this cylindrical wire, that is circle, pi r square. Area of cross section is pi r square. So this becomes the formula for Young's modulus. But this is the basic formula. This is the basic formula applicable to all the situations. But for this particular situation, when we freely suspend a wire, then we can write this also. So look at it carefully. Young's modulus is mg into L upon pi r square into delta L. Yes, Any doubt? This is a very different topic you have never done before. So look at all the terms very carefully. If you have any doubts, you can ask. All right. So let us do the second type also, right? Bulk modulus. Bulk modulus denoted by symbol K. Bulk modulus. It is again the ratio of normal stress but to the volumetric strain. The type of strain is volumetric here. So it is the ratio of normal stress to the volumetric strain. And the same situation we can take a pressure, normal stress is acting on all the sides of any object having original volume V. It gets compressed and its volume decreases by a factor of delta V. So that new volume becomes V minus delta V. So in this case, the normal stress is that pressure acting normally on all the sides. Directly we can write small p. And volumetric strain is minus delta V by V. So it becomes minus PV upon delta V. So this is bulk modulus. This is bulk modulus. Look at it carefully. Any doubts you can tell me.